All right, clip number 2 on Chapter 11, Section 5 notes on volumes of pyramids. In this clip, we're going to do 2 examples, one of which is a word problem, one we're given a diagram, but in both these cases, the new thing here is that I'm given the volume measurement for both of these pyramids, and I'm going to be asked to solve for some other measurable element in there. So let's attack it. This first example. One of the Egyptian pyramids, and this is a real life example, these measurements are actual real life things. One of the Egyptian pyramids has a height of 144 meters. For those that aren't in track and you're not familiar with the meter measurement, just a quick perspective here, that's over 1,500 feet tall. Okay, that's a big pyramid. So 144 meter tall. This, for the record, is going to be the altitude, height, depth, whatever you want to think of it as. This is going to be the H in our volume formula. Okay? And we're told it has a volume of 2.2 million cubic meters. That's important because that will be the capital V in that formula. So immediately, before I even continue reading, we are given 2 of the variables in that volume formula. The one that was not given to me was anything regarding the area of whatever shaped base this pyramid has. But since I do have the H and the V, I could just do a quick set of solution to find that capital B area of the base. We'll end up using that technique here. But then to the actual question, it says, find the side length of its square base. And that's significant, because it just told us the shape of the base. And that's something that's easily overlooked with these sorts of word problems, okay? Because fundamentally, in these volume types of formulas in Section 4, whether they're prisms or in this one where they're pyramids, the shape of the base fundamentally determines the formula that goes in for that capital B in our volume formula. The fact that it's a square, the area of a square is simply one of the side lengths squared. It's actually where the term squared comes from. Okay, so this square base, when I'm asked to find the side length of it, that's the only variable in that area of the base formula. So when I'm talking about capital B, area of the base here, it's just going to be side length squared. So that's going to be our strategy here to solve for that side length. Now, if it helps you to try and draw this or sketch this into a diagram, by all means, go for it. This would be a square base pyramid. So there would be 4 triangle sides to this pyramid that go up from it. It'd actually be probably the more familiar type of pyramid shape that you can think of when you associate the word pyramid. It would look like one of the Egyptian pyramids, the Great Pyramids. Okay, so in this case, if you wanted to sketch it, it probably wouldn't be overly difficult, but I do know that a lot of students tend to get intimidated by sketching 3-dimensional figures, let alone maybe something just as simple as a square. But whatever the case might be, we technically don't need the diagram. Let me show you. Now, the dead giveaway here is the fact that since we're in Section 5 on volumes of pyramids, I'm probably going to need this formula. Volume is 1/3 times capital B, area of the base, times the height, depth, altitude, whatever you want to describe it as, of that pyramid. And I am told pieces of information here. In the first sentence, they identified these 2 guys. The height or altitude of this pyramid was 144 meters. I can just replace or substitute 144 for H. Volume, I was also told explicitly, that was 2,218,800 cubic meters. Yeah, it's a big number. So what? You have a long number in your calculator. At that point, the one piece I don't know is this capital B, area of the base. The 1/3 technically is there, but I mean, it's just a number. And again, just bear in mind that 1/3 is, when I multiply 1/3 by something, that's the same thing as just dividing by 3. So if that helps to just think of it as dividing by 3, so be it. But in this case, what I can immediately do, the obvious first step here is to first solve for capital B, area of the base, which happens to be a square here, but we'll get to that in a minute. So if I'm solving for B, and this is really kind of the main punchline here of anytime I'm dealing with a formula where my unknown, the piece I'm solving for, is kind of in and amongst other pieces, I fundamentally need to move those pieces to the other side. This is really kind of the introductory basis of algebra, how to move objects across an equal sign. So let's move this 144 first. It's being multiplied by everything over here. So the way I'm going to move it is by the inverse or opposite of that, which is division. And even though it's a big number, I'm just going to do it on a calculator. So 2,218,800, there's that big number, divided by 144 gives me this gross number. I'm going to keep that in my calculator because even though I see this repeating decimal right here, what's actually going to happen is this: when I move this 1/3, it's going to clean that up a little bit. So I'm going to keep that number on my calculator. For the sake of writing something down, I'll put that 15,408 here on the side. 3 repeating decimal. But all I've done at this case, at this point, is I've just moved the 144. One step closer to getting capital B by itself. Next thing it needs to move is this 1/3. Again, if it helps you, this is technically the same thing as saying just capital B divided by 3, in which case it's a little more obvious what I have to do in that case. The opposite of division would be multiplication. I would multiply the other side by 3, which will then in turn get rid of this 3 repeating decimal. But if I still just view it as a fraction, the fraction is multiplied by B right here, meaning that I would divide the fraction to the other side. And anytime I divide a fraction, that's the same exact thing as multiplying by a reciprocal. That should sound familiar from your middle school days. But the reciprocal of 1/3 is 3/1. So when I multiply the other side by 3/1, that's just multiplying by 3. Okay? Whichever way you slice it, you're getting to the same conclusion. In order to move this 1/3, I'm multiplying the other side by 3. So again, I kept that decimal on my calculator. So when I move the 1/3 by multiplying by 3, I'm going to take that value and multiply by 3. I get a cleaner number. So that 46,225, technically square units, which are in meters, is going to be my capital B, area of the base. All right. So first off, just a quick note, why it got rid of that repeating 3 decimal. Repeating 3 decimal is the same thing as 1/3. So when I multiply 1/3 by 3, it makes a whole number. So that's where it went. Okay. In any case, we get to that result. Now, back to what the question's actually asking for. It's actually asking for a side length to this square base. What we have at this point, and if it helps you to sketch it out at this point, I have a square base. A square is a little bit easier to draw than a pyramid. And this is something that you would have gotten in a middle school type of problem. The area of this square, which normally we would put with a capital A, but I'm going to use the capital B here. B is equal to 46,225. That's the area of this square. And what I mean by this is like a middle school problem at this point, is that a square basically breaks down to one measurable dimension, a side length. Why is that the only thing I care about? Because technically all 4 of these sides have the same length. That's what makes it a square. So how do I find the area of a square? It's similar to finding the area of a rectangle. It's just length times width, but the length and width just happen to be the same measurement here. So length times width, or side times side, gives me side squared equals the area of the base of this pyramid. But since I can now replace these or substitute them, s squared is equal to that 46,225 that we just solved for. And at this point, what I'm being asked to solve for in this equation, in this question, is they're asking me for the side length, which is just s, which means I need to get rid of the squared. This is a newer operation that we've had to do in Math 2, but in order to get rid of a squared, I'm taking a square root. So the square root of 46,225 will give me my side length, and that may look intimidating, but it's just a number on a calculator. So 46,225. On my calculator, I have to do this shift button and the square root. Your calculator may be a little bit different, but look at that. It comes out pretty friendly. 215, the units here are meters. And the reason why it's just meters and not square meters or cubic meters is that it's a length. It's a side length. It's a distance. whereas the area of the base would be in meters times meters, or meters squared, whereas the volume are in cubic meters, because then you're also multiplying by another meter measurement, namely the depth. But there's my answer to this problem. Again, that's just a demonstration really of how to use inverse operations within the same formula. All right, we'll do one more example where we're now solving for a different piece. In this case, we were solving for capital B. In this next problem, we're going to be solving for the depth, or the altitude, the h in the volume formula. All right, so jumping back to our notes, this is the last problem we'll do for section 5. We're shown the following diagram, a triangular pyramid, but it's actually what we're told here in the problem as well. And just to remind you, the significance of that name, which in some of the problems they'll give you the name of the pyramid. When you name a pyramid, this part of the name, the triangular part, names the base. And that's important because when it comes to this volume formula of capital B times H, and then multiplied by a third, or divided by 3, that capital B is determined by the shape of the base. It's a triangle here, which means just like our first example from clip number 1, capital B will turn into 1/2 base times height for that base. So interpreting what we're seeing here, you'll notice that in this case, they have given us volume. So that would be our capital V in the formula. The triangle base is down here at the bottom of the pyramid, which visually speaking, that's most often the way it'll be shown to you. And they've shown us this little perpendicular piece on purpose. Because as I said in that first example in our first clip, for the area of a triangle, 1/2 base times height, it's important that the base and height are perpendicular to each other. So technically speaking, the 4 feet here would represent the base length of this base triangle, and the 3 feet would be the height of that base triangle. So in short, to find the area of this base triangle, I do 1/2 times 4 times 3. That would be the area of that base triangle. The altitude, the depth, the height of this pyramid is represented here, again represented by a perpendicular distance. So if I imagine this resting on the desk in front of me, the vertical height up to the tippy top of this pyramid is represented by that unknown h. So I can solve for capital B. I have capital V. I can now solve for h. So let's jump to the whiteboard. So in this case, again, volume of a pyramid, volume is equal to 1/3 times capital B, area of the base, times the height, altitude, depth, whatever you think of it as. And again, using the technique, I'm going to replace this capital B with the type of polygon shape that is in that base. In this case, it is a triangle. So capital B will be replaced by that area of a triangle, 1/2 base times height. Not to be confused with the other h being the altitude or depth of the pyramid. This will be the piece that we end up solving for here. So when I plug this stuff in, again, what I was told in this diagram was that the volume was 14 cubic feet. So I'll replace that with 14. It's called substitution. On the other side, I got 1/3 times 1/2 base times height. Base and height were both the 4 and 3 feet respectively. 4 and 3, it doesn't matter which order it comes in as long as they're perpendicular to one another. That will give you the area of that triangle. And then the piece I'm actually solving for here is the altitude of the pyramid itself, represented by h. So just like I did in the example in clip number 1, I'm going to kind of treat the fractions separately than my numbers. So 4 times 3 is 12. 1/3 times 1/2 is 1/6. And then h is still h over here on the right, and 14 still here on the left. So I'm going to go ahead and do these guys right here. 1/6 times 12, or 12 divided by 6, gives me 2. H is still there. 14 still here. Just finishing this problem off. Now, if I want to move this 2, it's multiplied by the h, so I'm going to move it by division. 7 equals h. The units here are feet, because it's just a distance, height, and altitude, however you think about it. But that's an example of how you'd solve this problem for the unknown height or altitude in there. Just a brief word on this. It is perfectly plausible for them to have algebraic phrases, like instead of saying like 4 and 3, it could have said like x plus 1, x minus 4. just use the polynomial multiplication in that case.